Hello Netra, can you hear me now?
Yes, sir.
Yeah, okay, fine. I think I think it will be better if we start the part on the last class and then in the end of the class, Jacobian. Now we'll start from the chemical potential. If she joins, I think it might be helpful instead of waiting for her.
Okay, sir.
Okay, fine. One second. So can you see the screen? One second. Yeah, can you see the PPT?
Yes, sir.
Okay, one second. Am I audible also, right?
Yes, sir.
Okay, fine. So this will be, I think, week five's problem session, and week five's assignment has been, I think, the due date is also passed, and I have gone through the assignment questions. It is more of partial molar properties, like 70% ethanol case, I think so. So and how to make the system solution and all the things. I think it has the same example problem as the sir discussed in the class. If you have solved that problem, I think. The problem which has given in the assignment will be easy to solve through, and so now in this class we will go through the week 5 module, I mean week 5 lectures, and I will give perspective of the same thing, partial properties and chemical potential, and at the end I will go through the PT diagram, I mean the rough way of PT diagram and Jacobian methods, and then followed by the next class initial points like phase equilibria. So before so now in this class, so these all are the basics which we already know. I'm not going much deep into this. So this class PPT more will be like a written way. So if you're not understanding anything in the written wise, you can ask me like, sir, can you rewrite? I will rewrite the things. So now in this class we will discuss certain things. I'm not sure. So we'll, oh, sorry, gone right. One second. So now my screen is visible, right? Yes, I think so.
Yes, sir.
Yeah, fine. So now the today's topic is, so now the today topics are of week 5. The highest one I will talk first. I will go through the chemical potential, then uh, partial molar properties, then I will talk about the Jacobian, I mean how to calculate the equation of states using Jacobian methods, sorry, the method, and then PT diagram, and then phase equilibria. I will start the basics of phase equilibria in this class if time permits. So now, so so we'll come to the chemical potential. So before going to the chemical potential, what I will write was, so I will first draw the mnemonic diagram just for my understanding. GHU equal to TdS minus PdV. So it means it is V, it is S, it is P, it will be T. So now delta G equal to VdP minus SdT. Yes. So we will derive everything from the Gibbs energy, because the Gibbs energy is the equation which has the temperature and pressure, which has a normal equation of states like where P, V, T. In this we have two things, so that's why we are. It will be easy to calculate for the Gibbs energy with time and pressure. So we know that dg equal to vdp minus sdt. If I write it in the another form, we can write it as dg equal to dg by t plus, so dp, the rate of constant pressure dt. So now it is for the closed system. If I have number of different components, then this same will be goes like t comma n plus, so here dp is there, you should remember that, pdp comma n plus d of g by dni such that p comma t ni is not equal to j. So here it will, so we are not taking the same compound, so that's why we are not taking I is not equal to j. If it is 1, then we are taking a constant as n2, n3, n4 and so on. So this equation we all know from previously. So if you know this equation, from this equation we says that this part, what do you call this part, as chemical potential. So this will be written as dg equal to minus sdt plus vdp plus sigma of mu I ni. So here it will be dni. So now what we understand from this equation was, so if you see any equations, like suppose if I say partial enthalpy or partial internal energy or partial entropy, they will all have what do you call what do you say, they will have the formulas of like SI bar or mu1 bar, not mu bar precisely, you can say VI bar and all things. But for the Gibbs energy, if I say GI bar, it is nothing but UI. So we will prove this one. So for today's class, we will try to give some theorematic way for this equation. So now what we will do was, so now our aim is, say suppose if this is the case, then what I am saying was, sorry, my bad, 1 second. Yeah. So what I meant to say was, here at constant temperature and pressure, say suppose I have taken one closed system with one barrier between n1 and n2, and it, as it is closed and I am not applying any external pressure, then it will be temperature and pressure will be constant here. So now at that case, so then if you take that case, the equation will be, if you are not understanding, you can tell me, I will explain it further also. So the equation which we know, this one will become as mu I ni. In this, if I am talking about at the constant temperature and pressure, then the G will become as sigma mu I ni. So if the total G is sigma of mu I ni, then the individual will be is nothing but a partial property. This we need to prove. So now I will prove this condition if it comes. So now let us take two component system. Two components means we have two different types of liquids. Say suppose that's all of G of T comma P and lambda n1 comma lambda n2. Lambda is nothing but a scaling factor, which is a constant value. So which is nothing but it is equal to G of T comma P n1 comma n2, as these all are the extensive properties. So now, so this is the basic equation which we are considering. So now what will happen was, if I apply both sides dg by lambda, so what will happen was dg of t comma p comma lambda n1 comma lambda n2 by d lambda, it is equal to d lambda of d lambda into g of t comma p comma n1 comma n2. So now if I'm saying d lambda, what does it says was it is a constant of temperature and pressure. So now, then if it is constant of temperature and pressure, the whole equation will go like so this is constant, so we will get how to say it. So now we are not considering this 2, so the lambda is here. So now if I write this whole as g, then g of, as there are two things, lambda n1 plus, yeah, d of lambda n1 plus d lambda. So this is one equation plus, sorry, into, my mistake, equals to g of, so have you understand this equation, how this equation came? Hello, if you can understand this equation, so I'm audible, right? Hello.
Yes, sir.
Okay, fine. So now we have this equation. So now the d lambda 1. So now here the n1 is constant. If you see n1 of d of g lambda 1.
Explain this
Which,
statement.
this one.
Yes.
Okay, fine. So what? So you know this equation, right? How from here to here this came, the right hand side. So I'm not talking about the right hand side because we are doing with the d lambda, and the lambda if you take, if you apply UV rule for this one, it is like uv dash plus vu dash, and so this will get because this is nothing to do with d lambda, so this will get cancelled, and d lambda is nothing but this. So here also same thing we are doing with so what I'm doing was, if you are doing with d lambda, what does it says was at constant temperature and pressure. So what I will do was, so now as g of t comma p comma lambda n1 comma lambda n2, say suppose if I give the equation of g of t comma p at constant pressure, what you will write was dg by dt at constant pressure, right? So in the same way, what I have written was dg by d lambda at constant temperature and pressure is equal to g of t comma p n1 comma n2, because this is obtained from d of d lambda of lambda into 0 of t comma p comma n1 comma n2. This is u, this is v, then it will be, this is the formula for derivation. So now if you do v dash, this has nothing to do with d lambda, so this will get 0 because this is the constant with respect to the d delta. And now here d lambda by d lambda, so this will get 1. So now here you will get g of t comma p comma n1 comma n2. Now this side if you come to the left hand side, so I think you can understand the writing part. So what I will do was, I will take, now I have two terms, one is dg by d lambda of lambda n1 comma lambda n2. If you remember, these are the two constants, so now I can write it like this: dj of d lambda n1 into at constant temperature, pressure and n2 plus dj of d lambda n2 into d lambda n2 divided by d lambda. This one, I am applying the chain rule for this. This one will get cancelled, so we will get the same thing. This is that. Okay, is this clear, this step? Hello.
Yes.
Okay, if this step is clear, then the next step is the simple one. So what we'll have is dj of d lambda 1 into d lambda n1 divided by n1 plus dj of plus, don't assume this is a subscript, this is lambda into n2 lambda into n1. So here it will be lambda, it is equal to g of t comma p comma n1 comma n2. So now we know that again if I apply UV rule here, d lambda will get cancelled. So now you will get n1 into dj of plus n2 into dj of so you know that if we have different system, this initially we represent it as a mu1, this as mu2 because we are differentiating with this component. So this is n1, it is equal to g of t comma p comma n2. So now we have sigma of I equal to 1 to k mu I ni equal to g. So this what we said it here. So if we prove this one, then the individual value of mu I will be nothing but the partial molar property of the Gibbs energy. Okay, so any doubts up to this?
No, sir.
Okay, so this is the how we can say that partial molar property of the Gibbs energy is nothing but the chemical potential. Okay, now if this is clear, now what we will do was, so now try to understand the system. Say suppose I will give a few examples which I read. One is you are taking the beaker, so I'm writing it here. So I have given, you have taken the beaker, there is water and there is ice cube. So now can you tell me the why the solid gets melted into water, and after some time if you keep it in the room temperature you will see these conditions, full of water, from solid water to solid liquid to full of liquid. So what reaction or what is happening here was so when you are talking about the chemical reactions, we are talking about the chemical potential. So chemical potential. So first I will make a statement, then I will try to prove it from the equations which you know. So what I'm saying was mu will always go from mu less than. So what does it says was, when you are taking two components, one is solid here, one is liquid, it will have mu s and it will have mu liquid. What does I'm saying was, mu liquid is always less than mu liquid is less than solid, so that's why the solid particles want to come into this environment. What does it means the chemical potential of liquidized water is less than the chemical potential of solidified water. So that's why the molecules which are here in the solid phase, we want solid region, wants to come into the liquid region. So if I want to prove it to happen the reaction, okay, I will give you the example. Say suppose we have H2O liquid form plus we have H2O in solid form. Say after some time, like after 1 second or 2 seconds, we have the same. Now assume it, if I want to put it like this, so we have n moles of liquid plus n moles of solid gives rise to, so now what we are assuming was it is increasing, obviously it will get decrease. Okay, any doubts regarding this equation? Just assume that number of moles of water in the liquid form and the number of moles in solid form, and after the reaction we all know that the solid will get melted to the liquid. So that's why the molar volume of liquid will get increased and the molar volume of solid will decrease. So this is what. So now any doubts regarding up to here?
No, sir.
Okay, so now what we will do was, so now if you take at this equation, 1 second, write it in the good way. Just searching for the good way. So now you know that, sorry, delta G of reaction is nothing but G1 plus G2. So which will take up the reaction of this side. So which will give as mu L dNL plus mu S dNS. So these both are same. It means one is decreasing and another one is increasing. So it means mu L of dNL minus mu of dNL. So now the more important factor is, so this will be the constant. So now the more important factor is mu L minus mu S, because we are talking about the partial mode. So that's why I have taken the Gibbs energy of initial, suppose G1 by G2, and I have taken the, it is equal to partial way. So if I am talking about partial, then it comes the mu I. So that's why I have written the mu L mu S. Now mu L minus mu S is there. So mu L minus mu S. We all know that delta G, to be spontaneous, it should be less than 0. So if it is less than 0, what does it says? Mu L is less than mu S. I will write it here again. So now we know that to spontaneous reaction, and delta 0 is equal to equilibrium.
Sir,
Yeah.
I can't see your presentation.
Okay, you can't. One second.
Yes.
Thanks for. Okay, can you see it now?
Yes.
Okay, fine. Thanks. Thanks for letting me know. Okay, now. Okay, one second. So now. So you have seen up to that, right? Where we have written. One second. So you have seen up to this one, right? How we got this equation?
Yes.
Okay, fine. Now, so we all know this is the case. Delta G is greater than 0. This is not happening. So from the example which we have, we know that delta G equal to mu L minus mu S. So if I take these conditions, mu L minus, to be spontaneous, I am writing spontaneous just for understanding, and then mu L minus mu S equal to 0, mu L equal to mu S, this is equilibrium, and so mu L minus mu S greater than 0, that means mu L is greater than 0, it's not happening. So not happening in the sense, we know that it is feasibly not possible to go from liquid to solid at a given constant temperature and pressure. So I'm not changing any, what you call, temperature and pressure. I just taken, okay, ice and water and kept it at the same temperature. So then we are understanding it. So we are not either increasing nor decreasing it as of room temperature I'm talking about. So if you see, for the spontaneous to happen, the mu L is less than mu S. So that's what we initially gone through. So if you take this one, so I make it statement, we all know that from here the chemical potential of liquid is less than the chemical potential of solid. So that's why in this, the, what you call, the solid molecule get liquefied. So suppose if I go into the another case, say suppose you have taken, you can understand this way. I have taken, okay, I will go to the PT diagram. So just remember this condition. So when can we say equilibrium was? So suppose, when can I talk about the equilibrium was? When mu of L is equal to mu of S. What does it say? Was when the chemical potential of liquid is equal to chemical potential of solid, then only it will stay in the equilibrium. So just remember the spontaneous and equilibrium. We will talk about this much further in the phase equilibrium conditions. So if you remember these two equations, we will talk much more about this in the, what you call, the phase equilibrium. So once we have this equation, okay, so now what I can do was, So you understand so any doubts regarding up to here? I think if there are
No.
okay, if there are no doubts, then what we can do so what we have done, so there is one more condition uh, which says that this is another say kind of, I will mention it as theorem. Mu mixture of T comma P comma of mixture is always less than mu of pure of T comma P. So what does it says was, so suppose if I have two component system A B, this is already there is a mixture, then I added A into this. Okay, so now we all know that, so as we see in the example of liquid and solid, where it says that the higher chemical potential will go to the lower value, here also it happen the same, the A will try to go to the AB. Okay, so this is what the proof, we can prove it. I will share you the proof with you. If you are not understanding after the class, try to understand the derivation. If the derivation is difficult, then I will try to explain in the next class. Okay, I think because this is not is it there, I think it's not there in your tutorial, I mean in the class, so that's why. So what we are taking was, I will just mention it roughly. So B A, assume it, this is the whole mixture, this is the pure component, we are taking both, and this is the membrane which is separating, and so here only this can enter this way because of this chemical potential. It can join until okay, once you attend this condition, this will not, the barrier will not be there. Okay, so then this automatically will be B comma A. Okay, so you need to remember this, and for this we have, so we know that, so here it is so it is B A, here it is PA, here it is, just for the sake of understanding I written it here. So now the total pressure of P total equal to PA cap plus PB cap. Say at equilibrium, so mixture of A is equal to pure A. So we will believe with me this, because we are saying the potential is same, then the pressure will be also same at these two conditions. So then we know that from the Dalton's law, equal to P total. So now mu A of mix comma P comma T, it is equal to, I am talking about the equilibrium, okay, equilibrium of this mixture and this one. So you will get RT ln of XAPT. Let me first complete the equation. If you have, I will explain it again. Mu of P comma T plus RT ln P RT, this is plus ln T XA RT. So now this will go to mu comma PT is equal to mu A P comma T plus ln of XA of PT. So you remember in the last few classes before, we have done this equation. Even in the Fugosity also we will do this. So have you remember this equation? Hello? I think so, yes. So once you know this equation, so from here what I written was at equilibrium, as I said, mu mix equal to mu A. So that's what we are planning, right, from the initial. At equilibrium it should be same. Sorry, mu dash of A is equal to mu dash A. So then mu mix of pressure total comma T, which is of the whole pressure, it is nothing but mu A of, now I am writing this like this. So now we get mu A of pure comma T comma XA P total, the pressure, so which is nothing but mu A pure comma T plus RT ln of XA into P total. So now so this will be goes as mu A PT comma TT plus RT ln XA. So this is nothing but mu mixture of P total comma temperature. So now if you see this equation, XA value is always greater than 0, so it means it will be this value is always greater than 0, so it means this is positive. So it means mu mix equal to mu A plus some positive value, so it means mu mix is always less than mu A. So that's why the particles in the A wants to go to the mixture. Okay, so it means whenever you are taking the equation, it's you need to remember this one. So when you are mixing two molecules, you need to understand which molecule is going to which side. So for that condition I am explaining, and from here you will get this equation also, G equal to RT ln XA, which is nothing but, okay. So I will send you the theorem of this in the what you call after the class. I will share you the drive. If you are interested in understanding this theorem, we can go through the module which I have given. If not understand, then I will explain it in the next class. Otherwise, if you have any doubts regarding up to here, you can ask me up to here. This condition I will send you the proof how the ZT equal to RT ln XA is coming. So as of now, if you have any doubts, we can discuss. Hello, am I audible?
Sir, how we are considering the last term is possible?
Which one? This one.
The last one. RTA ln XA.
So what I have done was, so at equilibrium we know that PA dash equal to PA. So if I am doing PA dash, for suppose PA dash equal to XA into P total, okay, XA into P total, which is nothing but a PA. So now whenever I am talking about the pure means you will get this one. So I will get RT ln PA. If you know the equation from here, it is nothing but RT ln PA, which implies RT ln of XA into pure T. So from here I got it to here.
Oh.
Understood that concept?
Yes.
Okay. So as of now, why we are discussing this was, say suppose if you are given any two systems, say suppose you have seen the phase diagram, or say suppose if you are mixing two molecules, say suppose water and oil, or if you are mixing any homogeneous fluids, or say suppose there is one clinical example which we discuss in the biological systems of, say suppose if you are taking the system with water and you have taken the skin of your body, it has the pores inside it. You know that you have the skin and the skin has the pores. So the chemical potential of the skin is less than the chemical potential of water here. So that's why what will happen was all the water in the tank wants to go into the skin. So that's why until it will go into it until it breaks down. So it will get breaks down. So this is one concept of chemical potential. So chemical potential, you can say that criteria for the chemical equilibrium is there are two conditions. If we want to get the spontaneous, the chemical potential of higher will always go to the chemical potential of lower. So this is one concept which you need to understand. furthermore, if you understand this concept, then you know basically that is z rt equal to minus rt ln xa. So this is second concept which you will understand. And how can you say that? Say suppose in the phase diagram, if you remember, we have this equation, right? I think you remember this equation. Hello. If you remember this equation, say suppose I say that I have two phases. We have done the example of, say suppose the water which is in liquid will vaporize. So then, say suppose I am taking the example of water. So then F equal to 2 minus 2 plus 1, which is 1. So if I take a triple point, which is F equal to 2 minus 3 plus 1, it is 0. This is two phase region. Yeah. So now if I take in two phase region, it is degree of freedom is 1. So you know this condition, right? We are talking in the initial classes. So how can you say one is in the two phase system? So how can you do the equilibrium? So whatever thermodynamics we are talking either in the spontaneous way or at the equilibrium, right? So when I say the equilibrium only, we can do the degree of freedom. So what? Okay, so these things will come further in the phase equilibria. We will extend the chemical potential basic concept in the phase equilibria with Le-Chatelier principle and I think Claira's equation. So from there you will get understand that much better way of how the equilibrium, how the chemical potential of, say we can talk about the water and how it is reducing. So this is the chemical potential with related with the degrees of freedom. Any doubts? Have you understand the basic concept which I am trying to explain here? The degrees of freedom and the chemical potential one.
Yes, sir.
Okay, fine. Thanks. Then comes the partial properties. Partial molar properties. So if you are talking about the whole property, which is G, which is nothing but molar property, but if I am talking about of a single component, so I suppose if the system has n components, suppose ethanol, water, I'm just out of curiosity I'm giving like x1, x2, not x1, x1 again will go to the mole fraction. Say suppose you have ethanol and water, the basic example in thermodynamics, ethanol and water, you have two component system. In the same way you can have the n component system where you have different n mixtures. So and you want to know the particularly of the ethanol or water, then comes the partial molar properties. So that's why we need to know about G1 dash. So now we all know that G1 dash is nothing but d of Ng by dn by at. So you know how this equation came? Is there any doubt regarding this equation?
No, sir.
Okay. So you know this equation from the chemical potential which we proved in the further class. So now I will write this as one general equation. P comma T comma Nj. So I am not mentioning any G or P, but you should understand that because we are keeping at constant temperature and pressure, obviously it will go for the Gi, but I have done. So now we have this thing. Now we will go step by step for the partial properties. Okay, now I have taken. So now if it is clear, I think we will take here and we will do it. So in this class mostly I will try to solve the the equations which was taught in the class so that it will be helpful. Sorry, again it comes. 1 second. So you can see the slide, right?
Yes.
You can see the slides, right? I think it is
Yes,
visible.
sir.
Okay, fine. Thank you. I think. So now I'm trying to. So whatever the Sart has discussed, I'm trying to give it in the derivation form so that it will be easy for you to understand. So that's why I'm doing this derivations. So now say suppose you have taken one property of moles, sorry, now we have, yeah, so I have taken n moles of m, and this is the equation, and m is the function of t comma p comma different components. So now if I apply, and I am applying the differential equation on two sides, so you know this equation, right? At p comma ni plus blah blah blah. So let me know if you are not understanding the equation, let me know. Okay, I will first rewrite all the equations. Xi equal to ni by n. You all know that mole fraction is nothing but the moles divided by total volume. So now if I apply the chain rule this side, it will be equals to, so you know this side, the n is constant this side, so I make n as constant here. So now okay, so this is the equation which we have. So once you have this equation, now I am taking all dm's into one side. So here you have the dp, right? You should understand this is the dp dt, this will be dni. Okay, so now what I will do is, so now I am writing one equation here. One second, let me, this is okay, fine. Now what I am doing was I am writing this as, so now it is n dm plus m into dn, it is equal to t comma x plus sigma of df plus x dm plus n into dx. Any doubts regarding this equation? I will explain it. Can you understand once like how this equation came from this to this? So x is nothing but, you can remember that ni, so I am not writing ni as ni again, so for that I written xi. So this equation is nothing but, if you see, so mi bar is nothing but mu I, sigma mu I, this is nothing but have you understand the concept, this equation, how we got this equation? I will write it in a good way. See, I'm on the screen, right? Hello?
Yes, sir.
Because I can't able to see whether I'm in online or not, so that's why. Sorry for that. Time t. Now, what I'm doing was, I'm writing this equation. As now, this will be, I can write it here itself. Plus so from this equation to we are going to this equation. Any doubts in this equation?
Can you explain the last term?
So this one, okay, fine. Remember this equation. Okay, so now what I'm doing was, so this is nothing but, if I given any equation, so this is, I can write it as d of ni, because Ni is nothing but, from here I can get Ni is nothing but xi into n. So plus sigma of mu I. So mi bar is nothing but mu I from the initial classes, if you remember. So dni is nothing but, so plus sigma of, so I'm keeping mu I as it is, so I apply chain rule here, so we got the chain rule here. So this is what I expanded it. So this is basically nothing but, if you see the initial classes, if it is there, I think I can show it somewhere. You mentioned the closed system, right? Okay, fine, I'll write it here itself. Sorry for the drag. So basically what we will write was dg as, so you remember this equation, right? So this
Yes,
one, so this one, what I did was, instead of mu I bar I kept the gi one bar. So gi bar is nothing but mi bar here, which we are taken in the generalized form. So ni is nothing but, so you know that ni equal to xi by n. So now, sorry, xi equal to ni by n. So that's why ni equal to xi into n, and d of xin is nothing but the chain rule. Okay, still any doubts?
under,
Understand that this equation, right? So
yes,
I just, what I did was I what do you call, I expanded the equation. After the class, if you try it on your own also, I think it will be better, because in thermodynamics, if you try the equations 3-4 times only, you can understand. Then, because I tried 3-4 times, so now what I will do was, I will take all the dm things one side, and n slides are all one side, and dn as one side. Now I want to represent the whole equation as n and dn. So now what I will take was, I will take n terms all to single slide. So I will write it down, so you can also write it and try it out. Let me know if I'm writing any wrong. So it is partial derivative, no, right? So I'm making, so any doubts in this equation? I will try it. You can understand my handwriting, right? I think there is no issues with the handwriting.
yes,
Okay, fine, thank you. So now what I have done was, so I have done with respect to the moles. So suppose if I increase the moles, and what type of molecule I have taken, or what type of component I am taking, what is the difference with the component. So this, with these variations, we can try to do it. And now once we have this, we know that we have two equations. This will be equal to 0. This will equal to 0. So now if I try to do these things as 0, let me know if there are any doubts in the equations. It will be easy for me to explain also. So dm, so now, sorry, I will write this as, so just assume that I am writing this as a and this as b. It will be easy for us. So this as c. So dm minus a minus b equal to 0. So here it is m minus sigma mi xi equal to 0. So here, okay, for the shortcut I have written a plus b plus c. You know that, right? A is what, b is what. It's at a at
yes,
constant t comma p comma x, and this is the d sigma 1. Okay, So now I have taken, I will take this equation. Now what I will do was, so we know that m is sigma of xi into mi bar. So now I will multiply by m. So now it is uh, hmm. So it will be nm equal to sigma ni. Any doubts in this equation from here to here?
No, sir.
Okay, thank you. So now we have this equation. Remember this and this. Okay, and this. Okay, now I will make one big equation from here. So now what I will do was, so now from the previous slide we have this equation. Sorry. So now we have the equation of sigma xi mi bar. So now I apply dm here. So it will be of d of sigma f bar. So it is nothing but dm equal to, if I take sigma out, so it will be d of, so now if I apply chain rule, okay, so this is the equation. You should remember dm. So now here we have one more dm. So previously I have written dm equal to temperature of, say suppose I'm just giving example. Another one is, if I'm not wrong, the equation is, so sigma mi bar dxi. Okay, so we have two equations with the same LHS. So now we can write the both are same. Okay, so now I will write as sigma mi bar dxi plus sigma di bar equals to, I think this will get cancelled out. So now you have minus sigma of, which is nothing but Gibbs-Duhem equation. If you go through the last classes, if you find that this is the equation of Gibbs-Duhem. So what is happening from the starting? So if you see, we have taken a system. If you see here, we have taken one system with the different components, and the changes in the components in the homogeneous phase will occur only if they satisfy this equation. Okay, this what we will get from the basic partial molar properties. Any doubts regarding this equation up to here?
No doubts.
Okay, thanks. So once this is done, so now we know the basic. I will explain the same this equation again. If this equation, I'm talking about this one, so I will explain it. So we know that if you understand the handwriting, you can let me know. Okay, I will change it. I will increase the sidebar or anything. Equal to x1 m1 bar plus x2 m2 bar. I have taken the only two component system. I'm neglecting the big large component. So now if I apply dm, so it will be goes like, so now if I take this Gibbs-Duhem equation, at constant temperature and pressure, what will happen was, if I take at constant temperature and pressure, this equation will become because at constant temperature this will get 0, at constant pressure this will get 0, sorry, this both will get zeros. So now you have this equation. So now it says what does it says was, okay, so now the addition of these two will be get 0, so it means this will go to 0. Any doubts up to here? I think, I assume there are no doubts. So the screen is visible, right? Just let
Yes.
Okay, fine, thank you. So x1 plus x2 equal to 1, we know the mole fraction formulas. So now if I take x1 equal to 1 minus x2, or dx1 equal to minus, sorry, wait, and show, my mistake. Yeah, you can see the screen, right? Again, I pressed something wrong.
Yes.
Sorry for that disturbance occurring. So dx2 so if I apply this here, in here, so it will be any doubts up to here?
No, sir.
Okay, so now what does it say was, if you plot the graph of m with respect to x, I will explain that also in the coming slide, you will get the slope as m1 bar minus m2 bar. So you need to understand this part from here. Just wait for 2 more minutes, I will give the better clarification regarding this. So now what I will write was, so we also know that m1 equal to plus m2. So now what I will do was, I want to write everything in terms of x1 x2. So if I'm not writing bar, you should understand that all are partial molar properties. Maybe sometimes I'm missing out. So if I write, so m in terms of x1 and m in terms of x2. So if you plot the graph of m with respect to this, so we all know that dm by dx1 equals to, so you proved here, right? This one, this I'm keeping it here. So now this is nothing but here if I write, so then this will become m equal to m bar minus, and same thing here. So now this thing I can expand it like full divided by x2. Sorry. So any doubts regarding this up to here?
No, sir.
Okay. So if I make the shortcut of g equal to g1 plus g2, just I'm giving one out of perspective example, you can understand like this. So if I take g1 and g2 as ideal gas situations, then it will be like ln p plus p1 plus, remember this as g1 plus g2. Any doubts in this equation?
No, sir.
Okay, so now this will go like RT ln ln x1 plus ln x2. Okay, so because x equal to p1 by p total, so now p total, just assume that. So this will be RT into ln of x1 p total plus RT ln of x2 p total. And now if I take p total as constant, then you have ln of xa plus ln of xb. So why I want to mention this was, say suppose you have seen the graph like this, right? Say suppose any I think in the tutor, in the SAR class, SAR has done for the x2, you will get, he has taken the tangent from there. I think you have seen this type of graph, right?
Yes, sir.
So I will come with the example in the literature. What I found out was, say suppose try to calculate this one, you will get this formula at the end, by the end of the equation. So uh, assume this is one property. Okay, now take, you can try it in the Excel sheet. If you take 0 to, sorry, don't take 0, take from 0.1 to 0.9 and 0.9 to 0.1, because it should be totally equal to 1. Now plot the graph of this value versus either this or this. You will find the graph like this. So this is from 0, this is 1, so this is 0. So you can think that, okay, why the graph is not going like this. Okay, so why? Because we need to understand the delta g equal to 0, then only the system will be in equilibrium. So that's why the equation will try to max to go down and then up. Okay, so that's why we have the curve in the graph. Say suppose, even though not only this, if you take the example of any say suppose of the volume curve also, sir, like what sir has explained, the graph will looks like this. If you take any experimental data, the same formulas and all the things, what you'll understand was, suppose if I try to mix the James Smith classical example, ethanol plus water, say suppose this is the, initially I have the system with ethanol plus water. After some time I have added the water of dw, a dw water molecule I added. So I started mixing it, and then it comes to the equilibrium. So now it is E plus W plus dw. I mean, this is basic representation. So as we all understand that, okay, as the volume should go increasing when you are adding x of water, and so mole fraction of water, I'm just writing like this. So initially it is here. Our perspective is like, okay, you are adding more, it means the volume also will go increase. But if you see the experimental data, there will be reaction happening, so it will go like this. That's the reason why we are taking the tangent, and then we are doing we are finding out the slope and all the things. So we will find this one. I think mostly we will find these values. Okay, you understand why the graph is like this? I mean, why it is not the straight line? If you see, our guess should be like this graph will go the straight as we are adding the more water. If you compare with the mole fraction, or if you think that, you can think that if I adding more water, it means the ethanol concentration should also decrease, but the ethanol concentration will also go like this. Okay, you can try to read any, I mean, if you find out any experimental data, you can, if you correlate, the best example of what why I said was, if you do it for the G, you will understand that at equilibrium it should be less, it should be less than 0, and it should be less than 0 if you start from 1, if you start from 0 to get the spontaneous reaction. So delta G should be less than 0 for the spontaneous, and at equilibrium it will be at equilibrium. So that's why the equation will go like this. It's not like this. Sometimes it can be like this, it can be like this, it never be like this or like this. So that's why we will take the tangents from here or tangents from here. Okay, you understand, right? Why the curve is curvature? No, I mean, why the graph is curvature?
Yes, sir.
Okay, fine. So this is the second concept. So once the second concept is done, 1 second. So the second concept is done. Yeah, we have still slides. I think you can solve easily the sum, right? The sums which were given for the fifth assignment, week 5. Any doubts? Okay, is there any? I see. Okay, fine. I think okay.
No.
So in the week 5 assignment, I think you just need to find out the volumes on the stuff. So you need to find the volumes only, right? They given the 70% volume ratio, I think. So no doubts regarding that. And I'll explain the fugacity concept clearly in the next week. I mean the week 6, where I explain the phase equilibria. Then if I go from phase equilibria to what you call there I will explain the Lewis-Randall rule also, then PVT behavior and all. So that's why I'm not explaining the Lewis-Randall rule now. So now, if you have no doubt regarding this, so I will explain the Jacobian ones, so that it will be there in the recording. If she has any doubts, you can watch it. Okay. I think week 5 consists of only this one, right? So your week 5 module is consist of chemical potential, partial molar properties, and the Lewis-Randall rule. Is there more than these three? The week, I think week 5 comes to week 5 topics are these three, right?
Yes, sir.
Okay, fine. So you want me to explain the Jacobian, or like we will go to the PVT diagram? It's up to you, because I think she is not here. So
Yes, sir, you can explain this Jacobian.
okay, so what? Why with Jacobian method is nothing but to get the Maxwell relations, or say suppose you know this equations, right? U equal to TdS minus PdV, or H equal to, I'm getting confused. 1 second. U equal to TdS PV. This is P. So now H equal to TdS plus VdP. So we can, and if I ask you to solve the H of t comma P, or U of t comma V, or S of t comma P. So initially we have done normally like Maxwell relation mathematical way. So the another way of doing this was Jacobian method. Jacobian method. I will go through the basics. Then I think so. If I say Jacobian of U comma V with respect to Jacobian of X comma Y, it is written as this is V. So this is nothing but determinant. So what I meant to say here was, if u is a function of x comma y and v is a function of x comma y, then the Jacobian way is this. Nothing but the determinant of these things, and the Jacobian has some properties. Jacobian properties. So what does it says was, if u comma u is a function of x comma y and v is a function of x comma phi, then d of u comma v of x comma y into equal to 1, and say suppose u is a function of x comma y and v is also a function of x comma y, and x is a function of r comma s, just sorry, a comma b, assume it in a small ways, and y is also a function of a comma b, then d of u comma v equal to d of x comma y into d of x comma y into d of a comma b, it is equal to, okay, this is the another property. And the third property we have was, this is the third property. So I can solve this third property. If you say suppose we have, so this is nothing but, you can assume that x is a function of a comma b and y is a function of a comma b, can be written like this. So now this is nothing but, assume that these are the properties. So this will be, if I take determinant, so this will be, so this will, one second, it's getting wet, dx by dA into dv by dv minus dv by dA. So I am keeping like this. So now I will do for the y comma x, because the both are the functions of a comma b. So then this will be, so it is nothing but Jacobian of x comma y. So sorry, something happened. Yeah, so I will write it here. I think this is better. So this is the third property. The fourth property is, so we write this one, right? If you remember, we are writing this a lot of times. Say ds by dt at constant pressure, or ds by dt at constant volume, or we know that dg by dt, nothing but v, sorry, p, I think, s minus s, sorry, minus s, and dg by dp as volume. So these things we can write in the Jacobian way as y comma a divided by x comma a. So if I put dg by dt s as, I can write it like this. So I will prove this one, what will come. So this should come like this, right? So now if I take a Jacobian of this, dy by dx, obviously this is at x, and dA, sorry, dy by dA at x. Okay, this is a det. So you know that a is a constant, so this will get 0. So this is a, right? Yeah. This will be 1, this will be infinite. So 1 into this minus 0 of infinite. So this will be, so this is what? Nothing but y comma a divided by x comma a. So these four are the Jacobian properties which we need to understand mathematically. Any doubts regarding these properties?
No, sir.
So now I'll make one second. So now assume that z is a function of x comma y. So then we know that dz equal to dz of so this can be written as so now we know that this two, now this I will change it. So now if I take the LHS common, if I send it to that side, the denominator one. So now this equation will be, now I want to put everything in the positive, so I am changing the inside things. So any doubts up to here?
No.
So then what we will do was, we will take this equation again, this one, we'll divide it by dB at constant A. They are the two different, assume it is a pressure and temperature, volume, temperature, anything. I have taken two parameters, I am doing this with this equation. So this will go like, so now I will make it as Jacobian way. B comma A plus Z comma X, Y comma X, Y comma A, B comma A. So now what I will do was, anyways B comma A will get cancelled, so now I will get X comma Y to that side. So equals to, this will be Z comma Y only. Because we have Y comma X here, if you see. So now if I put all together, so any doubts in this equation? Is equal to 0, sorry, here also it will be equal to 0. So what you need to understand was, here we have three terms. Say suppose T comma P comma V. I'm just giving the heads up. So suppose T comma P comma S. If I say the three equations you have, then T comma P ds plus P comma S dt plus here will be p comma t ds equal to 0. You can write it in this form. So basically x y z are same thing, right? S is a function of t comma p, because s is a function of t comma p. You can write it like this, or you can write it here also in the new term. Here you can write it as t comma p of s comma a. I will let you know what is a in the upcoming slides. You will understand it better. P comma s of t comma a plus blah blah blah. You understand, right? What this 2 does?
Yes, sir.
So these 2 are the important equations as of now. So this is the first equation you need to remember. This is the second equation. So now if you have 2 equations, and you need to remember one more thing. From the Maxwell relations, to solve all the equations, in the Jacobian we bring the new property, which is t comma s equal to p comma v. Just remember this only one. If you have this one, then you can prove any other Maxwell relationships which we get through. If you remember, in Maxwell we have done everything through reciprocation formulas. That you can apply from here also. If you apply to one side, say minus dt, but if I'm not sure. So if I take any one equation, say suppose from internal energy, you will get minus dp by so this you can easily prove it, minus of p comma v equal to s comma v. So we said that t comma s equal to p comma v. So this will go easily as minus t comma s to s comma v. So we are seeing that 2 terms equal, so keep this is also together, so it will become less plus of so any doubts in this equation? How the Maxwell relations can be obtained through Jacobian? You can try for anything. So suppose for Helmholtz energy you will get ds by dv equal to t. So you can even try this one also. So I will just give the example. It is nothing but which is nothing but this. So you can try this. In this way you can solve from this Jacobian. You can easily solve all the other things. Any doubts in this, how to solve the max? Okay, fine. So once you are done with Maxwell, so we also know so I think this will go as then we know that there is expansion and compression factors when you are talking about the volume of liquids we talked. So alpha slash beta, it will be I am directly writing the equation. So then compression is nothing but compression will be nothing but minus 1 by p okay. So these are the 4 equations which you need to remember. Cp Cv beta slash alpha k. Okay, so these 4 you mentioned here. Any doubts in Cp, Cv, alpha, beta, k?
No doubts, sir.
Okay, fine. So then next we can directly go. So now we have I will write it as beta, because I think initially also mentioned it, beta by k, it's better, beta by alpha, beta slash alpha, it's not by, so it is I think this is the equation. For k, the equation is now beta by k equal to 1 by p so this will get cancelled. Equal to v comma t. So now if I make these two together, so then so these two will get cancelled. So then I think this is the final equation. So I can, did I make any mistakes? Yeah, here it is minus symbol is there, right? So minus will be there, minus will be there. So now so beta by k, it's not slash. Okay, so it is, any doubts in this equation?
No, sir.
So now we can go now, say in the same way initially we have done, as I said, how to calculate s comma p and h of t comma p. So this I will write it as ds by dt at dt. I will try to do it for, sorry, okay, I will do for, okay, it will be easy only. So ds equal to s comma p t comma p dt plus s comma t p comma t dp. We know this is nothing but cp by p dt plus, so we know that t comma s is equal to p comma v. Why we are writing p comma v was in down it is p comma t, so we need to get one as constant. So from this we can get this as constant, so that's why I am changing it to v comma p, because my s comma t, right? So it will be v comma p divided by p comma t, it's a dp. So this is will be cp by t dt minus, so I will now I will make this thing to this side, so minus minus will get cancelled. I think I'm making any mistakes here. I think I make some mistake. It's still positive only. So now it will be positive. Now if I move it outside, it will come as positive. So now this will be dt minus, sorry, one second. Now if I write this equation here, minus of v comma t, sorry, v comma p. So this is nothing but dv by dt comma p is nothing but this equation. If you see this one, so ds equal to cp by t minus beta v dp. So any doubts in this equation? The equation is correct. Any doubts?
No, sir.
Okay, even once you can try also how to do it. So then we can get the relation between CP and CV. So the CP CV relation. So we all know that. So this will be the, I think, this time we have. Okay, so I'll. So you know this equation. So done now. CP equal to T of. So this is the equation. Now we have here, you can see we have S, P, T, V in the Jacobian. S, P, T, V. So we have the four properties. So four properties means we can come to this equation. We can directly write this one, because you can see that at A, constant A. So we have the constant P, constant V and all. You can see that both the equations will be matching. So now I will make this equation plus. You can also once try out. If you're not getting this equation, then you understand, right, how I'm writing this equation?
Yes, sir.
Okay, fine, thank you. So now what I will do is I will divide by T comma V and T comma V, such that I will get the equation which the desired one I want. So here it will be S comma T and P comma V divided by, I think here there is some problem here. Just assume that I think there is some board problem. One second, yeah, it's good. Okay, it's good, nice one. So T comma V will be cancelled, so that will be. So now this equation will be, so I'm writing this as same way. So I will write I will change this to V comma T, this to P comma T, plus this is ds by dt at constant volume is CVT, and if I change this to ds by dt at change, it will become as CPT equal to 0. So now I think this is the equation which we have. So CV, I have done anything wrong here? We'll see. CV CP plus P comma V divided by V comma T, P comma T. So now we know that from T comma S equal to P comma V, we can write CV is minus CP plus V comma P divided by P comma V to V comma T, P comma T. So dV by, sorry, is equal to 0. CV minus CP. Here we will get the expansion, the compression formulas again. If you see this one, dV by dt, this one will gives rise to beta V. This one will gives rise to beta by K. So now the equation will be beta V into beta by K equal to 0 plus, so it is CV CP plus beta square V equal to 0. Now CP minus CV equal to beta square V by K T. Any doubts in this equation? How the Cp minus Cv formula came? Sorry, it will be T. One second. I made some mistakes. It will be T here. It will be T here. Not this T. This T. So it is Bt Vk by T. So it will be not this one here. Square by K. No, it will be okay. Yeah. Any doubts? Now I made the mistake here because Cp by T equal to ds by dt at constant pressure. So we have this S comma P, T comma P will be this one. S comma P comma T comma P will be Cp by T. I made Cp into T. So that is a mistake I done. So I think other than this everything is correct. Any not mistakes. Any doubts?
No, sir.
Okay. So in the further class you can try h of t comma p with the how it solves the Cp minus C. If you can solve the somewhere you will get, if you can solve this through the Jacobian. If you're not getting, if you let me know in the next class, I will upload the module of this also. So I think she's not here. So you also have the doubt in this question. I will explain. Otherwise, I will explain to her because she has a doubt in this question. PV equal to PV graph, PT graph. Okay, I will explain it in the class where she is there. Okay.
Okay.
Okay. So now, yeah. So now I want to just give outline of phase equilibria. So it is third week's module, right? Phase equilibria. I think third week's lecture. Sorry, sixth week. Am I right? Hello. Hello. I think you are not audible. Hello. Hello. I think I am audible. I think. Okay, I think she has some issues. So if you see the phase equilibrium curve, I think I'll explain it in the next class itself. So I'll just give the outline of phase equilibria. So you need to understand that if you have the boxes, just assume you have the box of water and solid and the gas, solid and gas, and then yeah, I think the sixth week module is this one, right? Phase equilibria. I think if you go.
Yes, sir.
So if you, I'll explain it in the next class. In the next Tuesday will be the class is there for sure, because the last week I was some busy, so that's why I didn't take the class on Tuesday. It was shifted to Friday. And sorry for that delay. So the phase equilibrium, we need to remember if you take the PT graph, then we have, I will explain the mu T graph also, like chemical potential with temperature. So whenever you're reading the phase equilibria, it's better you should take the three boxes. Just assume you have solid plus liquid, liquid plus gas, and the gas plus solid. So you need to understand that the PT graph is nothing but you have P and T. This is the phase regions. So if I ask you to find the phase region degree of freedom along this line, so you know this is between the two phases, solid and gases, as this is the equilibrium lines, this all. So now I want to find for 2 comma C, it will be f equal to 2 minus 5 plus n, so it will be 2 minus 2 plus 1, so it will be 1. So what here also if you take same, it will be 2 minus 2 plus 1. At the critical point it will be 2 minus 3 plus 1 0. So what does PT diagram is doing was, it is converting a regions of solid, the solid, liquid, gaseous of regions, like we have solid region here, liquid region here, gaseous region, into a single place, so into single degree of freedom with two phases. So over this line, if you see this example, over this line the solid plus liquid are in equilibrium. It means what you can say was the system is of solid and liquid, it is in the constant phase. And if you see this line, it says the liquid and gases are in the same phase. And now if I take, so if I take this example itself, what will happen if I coming from triple point where all exist in the same, the liquid will exist, solid will exist, and the gases will exist. Now what I'm doing was I'm keeping the same system, just assume it in the normal way, then only you can understand phase equilibrium much better way with the equations and all. What will happen to the entropy, the volume, how does the entropy and volume changes, and what does the chemical potential changes. So we already says that I'm saying this line is at equilibrium, so this line is at equilibrium, and this line is also at equilibrium. So equilibrium means mu L equal to mu gas, here it will be mu solid equal to mu liquid. If this is the case, what is happening to volume, what is happening to entropy, which is big, which is small. And here also you can just try to understand in the basic way. Okay, I have taken the container, take the normal water, and I have taken the water and I have taken the container. What will happen to my system if I increase more pressure? So what will happen to the gaseous molecule, what will happen to the liquid molecule, and if I increase both, what will happen? So if you have this clear idea, in the next class if you have this idea, we will go through the further. If you have any doubts, we will discuss. Otherwise, if you want me to explain the any new topics or the not up to week 5, if you have any doubts you can ask me. You have any doubts up to week 5?
No, sir.
You need to, while studying the phase equilibrium, it's better to have the idea of how the entropy is different for solid, liquid, and gases. Okay, if you know this concept, how the ordered system will have the entropy, how the disordered system will have entropy, and which will be the more disorder compared to the liquid and vapor, I think this will give you the better idea. Okay, if you have any questions regarding the phase equilibrium, we will discuss in the next class. If you have no doubts, thanks for attending the session, and you may leave you can leave the class. Thank you for attending the class.
Yes, sir. Thank you, sir.
Thank you.